Okay, we're going to take another look at hydrolysis, and this is the second in a series of videos that I am going to use to go through this little chart and identify different types of molecules. And for this video, I'd like you to consider molecules that look like this one right here, or this one right here, or this one right here. This one as well. And so you'll notice that I'm specifically not including this one, or this one, or this one, or this one, or one that I don't see written on here. And most especially, I'm not including this one because this is a special one that I will do a separate video on as well. So if you look at the molecules that I have circled in blue, hopefully you can recognize those molecules and name specifically what they are. So if you're looking at those molecules that I circled on the previous page, you'll see I picked out this one, and I picked out this one, and this one, and this one. Those were the four that were indicated on that worksheet. And so clearly we can see that these all qualify as weak acids. So I'm going to set up a problem to determine the pH of a weak acid, and I may as well start with the first one on the list. Okay, when I look at a weak acid, I notice that the data booklet tells me that it is in a reversible equilibrium with its conjugate base. And so I see that represented in the data booklet, a weak acid and its conjugate base. In the data booklet, they aren't as specific as showing the water molecule on the left here, turning into H3O+. But rather what they do is they just show that this HF acid turns into H+, because the hydronium ion H3O+ is just like saying H+ in aqueous solution. So they just save a little time writing it out, because of course we know we wouldn't include water in our ice grid anyway because it's a liquid, so it doesn't have a concentration. So I've dialed it down to just the stuff that's in blue, and that's how I'm going to write them from now on, rather than being overly detailed and showing the full Bronsted-Lowry pairs of the acid and the base and the base and the acid. Once I've got that set up, I realize, of course, that if I have a 0.5 molar solution as indicated in the question, that I have no products to start. But of course, there's some amount of ions that will form in a 1-to-1 ratio, because in these Bronsted-Lowry equilibriums, it is always balanced 1, 1, 1, 1. And so I could set up my ice grid to reflect how much of that acid will actually dissociate or ionize, is the term we like to use for acids. And we're going to use the Ka value as indicated on your data booklet to figure out that dissociation amount. And so our data booklet indicates that the Ka value of HF is 3.5 times 10 to the negative 4. And now all we need to do is solve for x. Of course, we know that because this value and this value are going to determine what x comes out to be when you solve this equation, I can see that the 0.5 is quite a bit larger than my 3.5 times 10 to the negative 4. In fact, it is 1,400 times larger. So since the concentration of my acid compared to my Ka value is much greater than 1,000 times, I can feel confident knowing that this subtract x here will not appreciably change my result, and that makes this a much faster question to solve. I go ahead and solve that equation for x. I get the value for x, which represents the concentration of H plus at equilibrium, and I know that the pH is just the negative log of the concentration of the H plus at equilibrium, and so I find that answer to be 1.88. So you can see it's quite acidic. Now you'll see if I continue to do that for each of the remaining acids, the pH will come out quite different in each case, getting less and less acidic as I go down each of these examples, which means their pH will get higher and higher. And that is why you get a different answer for weak acids than you would if you were to just calculate the pH of a strong acid.